Okay, so I was asked to give an introduction, very short one, the intersection theory, which is, so this will be a classical introduction, and it won't work to transport the theory without any changes to our synthetic setting, because I mean, a lot depends on working over a field, and but the idea that we can then discuss, at least maybe you can get some definitions right, and I think that also that would allow us to actually test our theory. So, for example, let's take a classical result in intersection theory, Bezout's theorem. So when we have C and D in the two curves, yeah, so we define just by reducible polynomials. We are here over some field, two curves of degree D and E, respectively, intersect in D times E. Like a line intersects quadratic in two points. And intersection theory, well, makes sense of how to count points, and one can then prove the theorem. But the nice thing about this is, at the end, you get out a number, and numbers that we can compare. So, I mean,
so even if C and D are the same.
Yeah, then of course we have to make sense of it. So you have to try to move D, and we will see this in the talk. And so, I mean, when we have two lines, if they are the same one, we have to move one line, but the intersection number of two lines is still one, doesn't matter if we're moving it. Right, yeah, but when we want to use synthetic algebraic geometry to help classical algebraic geometers, then we think quite interesting, because we can transfer these numbers. Okay, so this is just one idea. So, and now let's start with just some topics. So one of the first is rational equivalence. X is a scheme of finite type over some fields. Okay. And then we can define cycles. And cycles, case cycles, are just normal linear combinations in I times VI, finite combinations. The VI are k-dimensional subvarieties. So, for example, zero cycles are just sum of points. And now let's take W in X k plus 1 dimensional subvariety, and let's say R is a rational function on W. Then we would like to define the zero set and the set of poles of this rational function, and it should be something like living in dimension. Okay, and this is what we do. So we define the divisor of R and plus the cycle of this. This is just the sum of all V of dimension K, and then we take the order at R at B, and I have to define this here. And this is something like the zeros minus the poles. So where R is invertible, so when R is invertible at the generic point of a variety, this is just 0. So this only counts the varieties here where this is actually non-zero. And that should define this. So the point is if we type if V W is a codimension 1, classically the local ring of V in W. This is of dimension 1. The local ring of dimension 1, and then for R, an element in its local ring, we define the vanishing order of R along W. So we take the module R module R, and one can show that this module now has a finite length as an A module. And the length of a module is the longest sequence of some modules we can get. And in case A is a principal ideal domain, one get back more, maybe better known versions of the vanishing order. Okay, so but the point is that we can, whenever we have a K+1 dimensional variety and a rational function on it, then we can talk about the vanishing order of this rational function along some codimension 1 subvariety. So in the simplest case, we should say W is everything, and yeah, say when we are on a curve, if X is a curve, then we choose the V's as points, so 0-dimensional. So W is our curve itself. Then we have a rational function of the curve, and then we count zeros and poles. The order. And then we can define rational equivalence, namely for alpha a K cycle, we say that alpha is rationally equivalent to 0 if and only if alpha can be is a formal sum of these principal cycles, so to speak. Alpha might be written as some kind of right of Ri, where Ri are represented on W I in the sense there. Okay, so some like this exists. And then the group we are interested in is ZAX modulo this rational equivalence. And okay, so why do we take this quotient? Why do we want to divide out anything? Well, so we here in this example. These curves in P2, they are just, they are elements in Z1 because they are dimension 1. And if we want to dissect 2, we have to be able to at least move 1. Otherwise, we cannot dissect C with C. So we would like to have some equivalence. I mean, actually, the theory becomes easier the more we divide out. Of course, we cannot. I mean, but of course, whatever we have to divide out has to be compatible with what we want to do. And think of this as homology classes. K-dimensional homology classes. And now, when one defines A star of X, this is just the direct sum over K of X. And some examples. So one is that a K of X is the same when we take the same scheme but with a reduced scheme structure. Because I mean the notion, I mean here the notion of subvariety does not change. When we reduce
subvariety, you mean closed, reduced, or
yeah, it's a closed irreducible subscheme. And irreduced. Yeah, because I mean irreducible is clear because otherwise I mean so if V has 2 components, V had 2 components, I would put them each component should define a class here. So we have this. Then maybe also simple, so a K of this joint union a K of this plus a K of Y. This is what we would like to have formally. And one can also define kind of short exact sequence or kind of mildly torus. So if x1 is 2 and x are closed, we have x a K of x1 intersected with x2, which is another, and then let's go to a K x1 plus a K x2 because varieties here are bet into x1 and also into x2, and the cocoordinate okay, now one can ask about the functoriality between these. And the first operation we have put forward. So that the x to y being a proper map, then if V and X is the subvariety, we can take its image called W and well, because it's proper, the gap is closed, so it's a closed subset of the image, and we can give it the structure of the variety. So this is again a subvariety. And here's where we need properness. But this is not enough to define the push-forward map, because the dimension can go down when we take the image. And if we view this as homology classes, K should not go down by pushing forward. And so the idea is just to throw out these things that have the wrong dimension. So yeah, what we would like to do is something pushing forward. This should be the image if the dimension of W is the same as the dimension of V, and it's F of V, thank you. and 0 otherwise. But this is still the wrong definition, because say if I have something like the spectrum of I don't know, some kind of field extension here, then the point here sits twice over this point, and I should count it twice. Or like more geometrically, when I have a Galois cover, I should add the degree for finite math. So I really need something like here the degree of E over W, and here actually where it comes in that I have to have the same degree, namely we define the degree here as we just take the degree of the field of rational functions of V over the field of rational functions over W. So, and I can view this as a subfield here just by pulling back a rational function, and because of the dimension being the same, I still well define the rational function after pulling back. I cannot, so the map here, we cannot then fully in the locus where the rational function is not incorrect. Okay, so now I can push forward, and then by linear extension we get this map, and one can show that this is, and that this works with rational equivalence. So we have an inducement on these childhoods. Okay, in a special case, which is used for counting, so if P is a structure map from the or scheme X to the point, and X is little k, and let's say this is proper, so X is the complete scheme. And say, let's say alpha being a zero cycle, this is just the number of points on X, closed points, together with multiplicities. Then we can then one defines the degree of the cycle by, can also call this an integral, we integrate alpha over X. And this is just we take it, where we go over all points, take the multiplicity of the point, all points in alpha. This is the multiplicity of the point in alpha, and multiply it with the degree of the field extension, and randomly repeat it over k, and this is nothing else. This is here nothing else as what we defined about alpha. So we just count the point. We just count points in a zero cycle, but we have to keep in mind the random repeat of these points, like here. And then formally we have the following rules. So f of x to y is proper. We can integrating alpha over x is the same as integrating over y, and take it forward alpha over y. Of course, just a form of consequence comes from functoriality. This, which the proof of which I statement which I skipped. Yeah, I mean, this here is just a number, and now basic. Well, if we would want to transfer the result, it need not be a number, because then we are still having cycles over our ring R. Our point is more complicated than just a spectrum field. So, and maybe so, yeah. Now, so this is about points. We also have something in the highest dimension, which is the fundamental cycle. So the idea is when I have a scheme X given by components xi, these are reducible components. Then say all of the same dimension. Then I can ask what the fundamental class of X is. And well, should be like the sum over all I. But as these xi here have to be reduced because they are subvarieties, I have to add multiplicities here because these components may not be reduced. And this I can formally define as the length of the local in here. Yeah, here let's count how far away I'm from reducedness of some component xi. So this also gives a link to homology where we also have this fundamental classes. Okay, now we have to push forward, and we can likewise define a pullback. But while the push forward is only defined for proper morphism, which basically due to the fact that our homology classes somehow have only compact support, the pullback is only defined for flat morphisms. So that needs to be flat of relative dimension n, and well, it could be like an open embedding or a projection, or it could be some say when I have an affine bundle, it could be the projection map to the base. These are all flat morphisms that are useful. And then when we have such a morphism, when we can define an upper star of some v at where we just take the free image of the horizon and take the image in Z, and this gives an upper star. So we have a class in Y, and because of relative dimension n, the pre-image, the dimension goes up by k, and one so that there is also sorry, this is x. One shows that this still works up to radical equivalence. Okay, so this is also what we want. We would like to pull back cycles along flat morphisms, and then we have the projection formula. So a lot of things I write down are quite formal, but I think this is basically the idea. I mean, we'd have to try to make it formally work, because then a lot of things just also follow formally. So the projection formula, well, we have the following situation. We have x, y, and is proper. Now we have a flat map. Y prime, g, so this is flat. And for the g prime, it's f prime, and the base changes are flat and proper, respectively. And then we can take a cycle alpha here. And I can pull it back by flat morphism. Sorry. Alpha here, and push it forward. And I can do the same the other way around. Forward and call it G. Up star, this is the same. So this behaves so now it behaves well with respect to flat base change. This is yeah. And one maybe wrap down this. We also have some simple exact sequences which still use for different things, like when we have the y and x closed and u being a complement, then we can when we have the following sequence even after rational equivalence from AKY with AKX to AKU to 0. So this is exact. And I mean, you can write this here. And as always in homology, we have an exterior product which is, so when I have something on X and I have something on Y, I get something to degree K plus L in the product of X and Y. We're just taking a cycle here, pulling it back onto the product, which I can do because it's flat morphism, and yeah, and then adding some whatever comes from here, and this gives me something here. And this is the exterior product. And to define the intersection product, we would like, so if this is X and this is X, then I have X times X here, and now I would like to restrict to the diagonal. So this is the idea. But I cannot with what I wrote down here because I'm pulling back along the diagonal. I mean, the diagonal is very far from being flat. But then I would have intersection of two cycles. This is the idea. Yeah. Okay. Okay, now so these are homology classes, and now we come to something that looks more like a cohomology class, which and these are given by Cartier divisors. So you already saw them. So Cartier divisor is given by the datum. I have an open cover U alpha, and I have elements F alpha or and F alpha are just rational functions over X, and let in this case be X irreducible of dimension N. And these rational functions, the quotient of 2 should be an invertible element on the intersection. And yeah, so now if these Cartier divisor, I can define Also, where it can yeah, you can define the order of the Cartesian divisor along the subvariety V of but just say that the vanishing order of this rational function along V, and it does not, I mean, now depending on whether I take F alpha or F beta when I'm on the intersection of U alpha and U beta, but it won't change the vanishing order because the quotient here is invertible. So this is well defined. And this order is defined by these are rational functions on X, so V should be n-1 dimensional. And well, this defines a cycle associated to T, which is just given a go over all n-1 dimensional subvarieties and multiply this by the order, and then have z-1 over X. And these here are by definition the Weil divisors. These elements, and so what we get is here, this is the group of Cartesian divisors, and we have a map to the n-1 X, to the Weil divisors by this construction. And well, we can now here divide out a-1 times a-1 of X. Here we divide out rational equivalence. And here we can divide out something similar, which is called linear equivalence. You can get the PK group. The point is that we can use these here as a gluing datum for a line bundle, for an invertible sheaf. It's a chain code cycle in all star. So this gives the line bundle, and this is called linear equivalence, going from here to here. And this, when we do this, well define upper rational equivalence here, this map. And well, the idea is this is homology, this time in degree 1, this is homology in degree n-1. The picture. So here we have the homology. And maybe that's a remark. X is normal, respectively locally factorial. So all of those rings are factorial. Then the map of the devices, so the Cartesian devices to the Weil devices, and also the R of X, so once Chow group of X is injective, respectively, small. So, I mean, in general, this is a different thing, but yeah, for nice scheme, you have to say. Okay, and yeah, we already saw calculation of the PK group for Tn today, and well, it's, in this case, we have to say. Okay, now a topic which is called pseudo divisor. The problem is that we cannot really pull back the Cartesian divisor. So if we have just any map, it may not be that pulling back all these F alpha give rational functions after pulling back, because in general I cannot pull back rational functions. What I can pull back is a line bundle. So the idea is, Cartesian divisor is something like a line bundle plus a section. So if we have a poster, this gives me a section. So I should consider line bundles plus sections. And now when I pull back the line bundle, it can happen that I still have a section, or that the section is no longer defined on some, is nowhere defined. So what is a pseudo divisor? Is the triple consisting of L, Z, and S, where L is a line bundle, Z and X is closed, and S trivializes L over X without Z. So then nowhere vanishing section. So this is what a Cartier divisor gives me, and that's of course dimension 1 for a Cartier divisor. But now what can happen is when I pull back, that Z becomes everything, which is allowed here for a pseudo divisor. And then well, we call this also OE, the associated line bundle. This we call the support one the section. And okay, I won't say much more about this construct, but the idea is we can relatively easily generalize Cartier divisors to something that we can actually pull back by remembering where it's defined or where it's not defined. So what we get is when we have a pseudo divisor, we still have a class, and the class can be made can be defined by subvarieties living in the here. And okay, no. Pseudo divisors pull back. That's what I find. Okay, and now we can start to intersect things. Because when we have homology classes here, and homology classes here, we should have some kind of cap product. This is what we get. So intersection, so if P is such a pseudo divisor, and you have B and X for the morphism J, a k-dimensional subvariety. We can define the intersection of D with V, so the cap product. Well, what you have to do is we pull back the divisor D by J, which we can do because it's always well defined. And on the line bundle side, we just pull back the line bundle, and then we take the associated divisor of it. And then we get something which lies in A k minus 1 of what? On the support of the cap B. So this is, so the idea is we can intersect by line bundles, which just amounts to putting them back. And then we have a bit more information, we can also do the section. And then we get something like this. And this here is actually, so this construction is compatible with pullback, and we also have a projection formula. Maybe let me write it down. Which says that pulling back D times alpha, putting it forward, is D times alpha with F. A suitable map, and alpha and D divisor and a cycle on the correct on the right space. And then we have the following theorem. So we can take a divisor D prime, Cartier divisor, or let's say pseudo divisor. Then we can take the associated cycle and take a product with another divisor. But this is not a priori, this is not symmetric, but the theorem says it is. And so, as a, and we can show, and the corollary from this was not clear, along from this definition, is that intersecting with D gives a map from AK to X times AK minus 1x. I mean, here I have a subvariety, but here I just consider subvarieties up to rational equivalence. And using the theorem, one can show that this is actually well-defined rational equivalence. Okay, and one other corollary is, of course, that D1 times D2 times alpha is the same as D1. Okay, now we can already somehow see the intersection on Riemann-Roch's theorem, because there we just have two classes like here, and if the two curves were represented by line bundles, no, Cartier divisors, then we can already multiply these two. And okay, now we can introduce channel classes. When L over X is a line bundle, and it's much simpler than a topology in some sense. So if L over X is a line bundle, then B is a subvariety. We define the first term class of L as an operator. So the first term class of L operates on the cycle of B. This is just C, the fundamental class of C, where we take L, the line bundle, restricted to B, that is a line bundle on X, and this is O of some Cartier, O of C of some Cartier divisor. And then we take just the associated Bay divisor. Okay. So what we get is one of L. So that's also basically we just L defines Cartier, or L is given by a Cartier divisor, we just intersect by the Cartier divisor. This is just the first Chandler's operation of a line bundle. And so this goes from AKX to AK minus 1 of X. And we can already see few formulas for the first Chern class. For example, the first Chern class of the tensor product of two line bundles. Well, I just have to see what happens here to the tensor product. This is given by the sum of two divisors. So this is just C1 of L plus U of L. Sorry. And an example which we actually can, so this is what we could do as well, because so LK is a k-dimensional linear subspace. And then what you can do is we take C1 of O1, we know what this is, and then we intersect with this class. Well, this just means restricting this line bundle to LK, and well, this gives again O1 on LK, and this class is just LK minus 1. Yeah, because the intersection in O1 over LK, then it vanishes along an LK minus 1.
So what is LK?
K minus 1 dimension linear subspace. So I mean, if I have a Pn, I would like to write down elements for the tau groups. So I can take a k-dimensional subvariety. It does not matter which one because all are rational equivalent. Linear space as a linear subvariety. I intersect with this here, and then I get just one. Yeah, and this also allows us to define the degree. So if alpha is in K of Pn, we can define the degree of alpha, because we take C1 of O1 k times have alpha, and then we are down to a class of degree 0, and this we can integrate. And geometrically, this means we just intersect with k hyperplanes and then count numbers. So this is how we can count. Okay, so maybe I can skip this. So now we have the first Chern class, but of course we would like to have higher Chern classes as well. But when the first Chern class is something we can write downward strictly in line bundle. And one now takes a detour via SAG classes. And so we have a vector bundle E over vector bundle of rank R in E plus 1. And we take the projectivization of this vector bundle. Fiber-wise projectivization, so we have PEs over R. And now we can, now here we have E over X, and here we have P upper star by pulling it back. And we have the topological subbundle, O minus 1, which we saw at the top before. So there's a topological sub-bundle. And now we consider the following iteration. We take a class AK on X and go to class AK minus I on X by the following operation. We take alpha, we pull back alpha. I mean, this morphism is flat, so we can pull back it. Now we are on the projected space. Now here I have a bundle, namely O1. I take the first Chern class, and now E plus 1 times I intersect with this class, and again I push forward, which I can do because this map is also proper. And now some counts the dimension right, and then it goes down by minus pi. Because of this here, and the E just can't the pull back here. Okay, and this is called the operation of the ith cycle class. Okay, and we have a number of propositions. So as I equals 0 for I being less than 0, and B the identity of this, and then we also have C that when we take the operations, it doesn't matter in which order we take the operations. And we also have the projection formula. It's pullback compatible, etc. And for line bundle, so when I have a line bundle, then the first vector class over alpha, this is just -1, Chern class alpha. Okay, so this more or less geometric operation here, because this is just intersecting by fiberglass hyperplanes. Geometrically happens here. We can define the Chern classes. Namely, what we do is we define the total sector class, which is just the sum over the SI. And this, so it starts with 1 plus S1 of P plus 2 of P, and so on, because the first one is the identity. And now I take the formal inverse as a power of series. I mean, these are getting smaller and smaller in that topology, in which I invert this. And if we do this, we get 0 is 1, C1 is minus S1, C2 is S squared minus S2, and so on. So I get polynomials in this, when we just formally inverting this series, get polynomials in the second classes, and the total term, and now the main point is that the ith Chern class of E is 0 for I being bigger than R. So we only have something up to dimension R. Okay. And now so these are still operations on our child group, so on our homology classes. And from this we can define other classes. The Chern character, and by the following trick. So we formally write C being 1 plus xi over I. So C is just the sum over all these. And when I write this, I interpret the kth Chern class as the kth elementary symmetric polynomial in the xi's. So now whenever I write down something which is symmetric, like this here in the xi's, and these are the so-called Chern roots, by the fundamental theorem of symmetric functions, this is actually an expression in the Chern classes. I mean, we can write down what the Chern character is. So why is this interesting? This is because, I mean, this follows very formally. If I take now the tensor product of bundles, then this is just the product of the Chern characters, just by using exponential function here. And what's more, the Chern is additive in short exact sequences, in short exact sequences. And I can also find the top class, hot, which this is given by the product over xi to 1 minus e to the minus xi. But this is obviously symmetric as well, and this is multiplicative in short exact sequences. Now, what is this good for? Okay, now I have to choose the topic because maybe just say one thing and then I can say more to whoever is interested after the talk. So now we have two more things. One can say at this stage. The first is, trying to define intersection between two homology classes, seems the diagonal, and linking this to the talk about Riemann-Roch we had to do before. And this is, I think, what I will do, and then we can just talk about intersection of classes a bit later. Namely, so and the generalization is Grothendieck-Riemann-Roch, which we can formulate now. So on one hand side, we have, so in this case, let's say x, y, smooth, proper, between smooth varieties. And what k upper 0 of x is just the Grothendieck vector bundles. So formal linear combinations of vector bundles modulo short effect sequences. So then the modulo, yeah, so yeah. And well, because the germ character is additive with short effect sequences, it's well defined. Going from the germ character here to a star of x. Well, the germ character has q coefficients, so as the tangent is just q, out of the exponential function there. So, and this here is actually, this is a ring homomorphism. What I wrote down here. This follows formally. And this ring homomorphism is compatible with fullback. The whole. This follows the from construction of the giant garden, for all this compatible by fullback. And now one can ask, is this also the ring homomorphism compatible with push forward? So I can try to push forward this and take a push forward here. And I can ask whether this commutes. And well, now first of all, I have to define what is the push forward of the vector bundle here. And the idea is just that I have to take, in order to make it compatible with short effect sequences, I have to take the entire direct images of E and F of all I, because otherwise it's not compatible with what I divide out here in the K group. And one also has to be a bit careful. So this is the image of the vector bundle is in general just a coherent sheaf under a proper map. But as we are on the smooth scheme, I can resolve a coherent sheaf by vector bundles again. So I still get a well-defined element in this K group. Well, and now the answer is this is wrong. But the result of Grothendieck, so he said, well, let's check how to repair this. And well, the point is, when I take the giant character, pull it down, it's not quite the same. Taking the giant character, put it down, but we can repair it. We have to multiply here by the top class of the tangent bundle of y, and here we have to multiply by the top class tangent sheet of tangent bundle of X. So this is a statement of Grothendieck-Riemann-Roch. This is just, so this is a lot of formula, because in here we have just a formal power system. This just shows up through some formal calculations with. And then we have corollary, which is principle Riemann-Roch. Here we have just y is a point. And now what does it mean? So on a point, we have no tangent bundle, so this is just one, this vanishes. And what is the push product here? While taking higher direct images of a sheet to a point is just taking the cohomology groups. And well, the K group of a point is just given by virtual dimension. I mean, just take alternative sum of the dimension of the vector space over the point. So this here over a point is just the Euler characteristic. We are multiplicating sum of the dimension of the cohomology groups. Here, on this side, x p. Well, here I put forward to a point, so this is just an integral, and then I find out none of e times log of c x. So this is principle Riemann-Roch, and now let's restrict it to the case of a curve. So on a curve, and let's say P is a line bundle given by divisor D. Then on this side we have the number of sections of OD times A1 C OD. And what's on the right hand side? Well, Churn of E is 1 plus C1 of E, also OD, times, and the top is, well, we can calculate this just by plugging it in, and comes out that this is C1 over 2. Now we integrate over a curve. To integrate over a curve, I need a cycle of dimension 0. So this has codimension 1. This is codimension 1, so it's this plus this. But C1 of OD is just D, integrating gives the degree of the divisor. So we have the degree of the divisor. And here we have C1 of the tangent bundle, which is minus C1 of the cotangent bundle. And with some curve theory, this is just then 1 is 2 minus 2G. Genus, or we can just define the genus by integrating C1 if you want. And so we get 1 minus 2. So this is just this innocent result is actually comes from this Marc generalization. This, I mean, made more easier to access in the sense that a lot of things until we come here are formal. So we have to sum up. Of course, and it's also we are also here in a relative situation. I mean, here I need that I'm over a point, and I have dimensions I have to count. It's a bit unclear for spectrum of K's in our case, but here we have a relative situation. Okay, yeah.
Mentioned the zoo in the beginning. Can I extract it from?
No, not from this. I mean, this I didn't something. I didn't plan to build this. That's I mean, you can use these things to make sense of both sides of the zoo. I mean, you have two curves, and I mean, now the question what is the intersection? And this is what we saw. We can, yeah. It's so we one curve we realized that the zero section of a line bundle. the support of the zero section of the, no, not zero section, of the support of zero load of the section of the line bundle. Yeah, then restrict this line bundle to the other curve.
Yeah.
And then we count on this curve, because we get the divisor, take the degree, and this is now the number, the intersection number.
Mhm.
And then what I showed on
The zoo holds is something I still have to compute.
yeah. At one point you still have to compute, but it's not. I mean, you can do a lot by hand. So I mean, say if I have a line and a curve of degree d, it amounts to restricting the equation for the degree d equation to a line. But now you have to calculate the number of zeros of a polynomial of degree d. And this is d. I mean, the difficulty comes in that what do you do with multiple zeros? And yeah. But and you can do yeah, but you can do this by I mean, it depends on how you define the degree. So if you define it by hand, just taking the degree of a polynomial, you have to do some calculations by hand. But I also define the degree of the cycle using intersection with the first Chern class. That well, when you have a cycle alpha, you intersect with hyperplanes until you have something of degree 0 where you can count, and then you call this a degree. And if you define the degree of a curve like this, then you get immediately Bezout for the curve and the line.
Yeah.
Yeah, and then the rest can follow from it. You can extract formally. Yeah. But and you may also want to take a look into the appendix of Hartshorne, where he writes down just 7 axioms that the Chern classes have to, that they do fulfill and have to fulfill, I mean, in order to state all these things. And so the basic ingredient is, well, calculation on the projective space or on projective bundles, that you know how the Chern, how these Chow groups between the base and the total space of the projective bundle relate to each other. So this is what you have to understand, and then you can do that.
So you mentioned that the Chow groups play a role similar to homology.
Yes.
Is it actually an homology theory in some sense?
Where you can, so when you're on a complex manifold, you can map this to homology groups, but just taking, I mean, the subvarieties define fundamental class in say, Borel-Moore homology. And then you can just take the image. So you can compare them. And I think you can do the same in Algebraic homology. Well, but here we don't divide out a lot. I mean, you just divide out rational equivalence. And in general, these are infinite. I mean, these are infinitely dimensional. These, like in homology, we divide much more. Mm-hmm. So I'm not so sure. Yeah, I mean, there are people who calculate these things. I mean, just to get at the end to get numbers, we don't need to calculate these. Yeah, but can use. But maybe this is not nothing we have to do. Maybe it's just enough to know that there are some of these groups, and we have these operations. Yeah, and at some point we have to divide out rational equivalence, because otherwise some operations wouldn't have been well defined. We had to divide out something, I mean, this is hidden as a proof that it yeah. So maybe an answer to the question is, yeah, well, if you call something that behaves like linear homology theory, then we have one.
Very good. Okay, so we'll finish it again. Let's have a break.